What if Voyager 1 has not simply entered interstellar space, but crossed into a region that our old physics books could not properly describe? And what if the strangest thing it found is not silence, emptiness, or darkness, but a hidden structure, still reacting to the sun from billions of kilometers away? Before we follow that signal into the unknown, tap like, subscribe, and share this video with someone who thinks space is empty. By the end, you may never look at nothing the same way again. Voyager 1 was launched on September 5th, 1977. At the time, its mission sounded ambitious, but limited. It would visit Jupiter and Saturn, photograph their moons, collect data, and then continue outward. Nobody could honestly promise that the spacecraft would still be working half a century later. Nobody expected it to become humanity's first direct observer of the space between stars. Voyager flew past Jupiter in 1979 and Saturn in 1980. Then it kept going. It passed beyond the planets, beyond the familiar map of the solar system, and into a zone where the sun's influence slowly weakens but does not suddenly disappear. In 2012, Voyager 1 crossed the heliopause, the boundary where the solar wind gives way to the surrounding interstellar material. That moment is often described as entering interstellar space. It was historic, but it was not the end of the story. In a way, it was the beginning of the most important part. Voyager did not step through a clean door. It moved through a complicated transition zone, a place filled with changing magnetic fields, waves, pressure fronts, and invisible disturbances. Today, Voyager 1 is roughly 167 times farther from the Sun than Earth is. That distance is difficult to imagine, so here's a better comparison. A radio message traveling at the speed of light takes more than 23 hours to reach the spacecraft. When Voyager sends a measurement, Earth does not receive it instantly. The answer has already been traveling for almost an entire day before anyone can read it. Yet the signal still arrives. It comes from a transmitter producing only a small amount of power. This power is comparable to the energy used by an ordinary household light. By the time that signal reaches Earth, it is incredibly faint. Giant antennas belonging to NASA's Deep Space Network listen for it from locations in California, Spain, and Australia. They collect a thin whisper from the edge of the sun's neighborhood and turn it into data. That data is now showing scientists something unexpected. The region around Voyager is not a smooth, quiet ocean of gas. It is more like a layered shoreline, shaped by waves that began near the sun and traveled outward. These waves struck the heliosphere and continued into interstellar space. The old picture suggested a boundary followed by calm, undisturbed space. Voyager found a boundary followed by more boundaries. Before Voyager arrived, scientists had to build models using distant observations and theory. Those models were useful, but they were also limited. Imagine trying to understand the waves around a harbor while standing on a mountain many kilometers away. You can see the broad pattern, but you cannot feel the small currents, measure each ripple, or know how the water changes below the surface. The heliosphere was often represented as a bubble pushed through the galaxy. The sun releases a constant flow of charged particles called the solar wind. That wind expands outward and creates a huge protective region around the solar system. Far away, it meets the interstellar medium, the extremely thin mixture of plasma, gas, dust, and magnetic fields between stars. The simple drawing showed a bubble with a rounded front and a long tail behind it. The outer edge appeared to be a reasonably clear surface. Cross that surface, and the sun's domain would fade. Beyond it, the interstellar medium would eventually become calm. But space does not respect simple drawings. When Voyager crossed the heliopause, its instruments recorded changes. These changes confirmed it had entered a different environment. The particle population changed. The magnetic field shifted. Plasma waves appeared. But the transition was not as clean as many models suggested. The field did not simply snap from one direction to another. Instead, Voyager encountered a zone with layers and lingering effects. This matters because a boundary is not always a wall. It can behave more like a membrane. It can move. It can bend. It can transmit pressure. It can carry the memory of an event from one side to the other. The heliopause is not just the edge of the solar system. It is an active interface between two enormous environments. The first major surprise was that the sun could continue influencing space far beyond the place where its ordinary solar wind ends. Solar eruptions can launch huge clouds of magnetized material, called coronal mass ejections. When these disturbances travel outward, they expand and weaken. Scientists knew they could affect the heliosphere. What Voyager showed was that some of their effects could continue beyond the heliopause. In the years after the crossing, Voyager detected waves and compression events in the interstellar plasma. A solar outburst could make this material outside the heliosphere react like a bell. The original explosion happened near the sun, but the echo reached a spacecraft more than 100 astronomical units away. That image is worth holding on to. The sun can erupt and the disturbance can cross the planets. It can reach the outer boundary of the solar system, push through that boundary, and still be detected by Voyager years later. Interstellar space is not isolated from us. It is connected to us by pressure, fields, and waves. One of the most revealing discoveries was not a dramatic shock. It was a persistent plasma hum. Voyager's plasma wave instrument detected a narrowband electromagnetic emission that continued in the background. It was not just a one-time response to a solar event. It acted like a faint, ongoing vibration. That hum gave researchers a way to estimate the density of the surrounding plasma over time. Instead of waiting for a rare shockwave, scientists could listen to the background and track how the medium changed. The result was not a perfectly constant density. It varied across distances of about 1 astronomical unit. Those variations suggested that the very local interstellar medium, or VLISM, has its own turbulence. The region is not simply being disturbed by the Sun. It also carries the influence of the larger galaxy. The Milky Way is not a silent backdrop. Its magnetic fields, moving clouds, and large-scale flows help shape the environment. And this is where the story becomes more surprising. Voyager is not passing through one uniform region. Researchers have identified a sequence of structures and events in its path. There were shock waves and pressure fronts. They found changing magnetic orientations and a long-lasting feature known as the magnetic hump. The name sounds almost harmless. The event was not. Around 2020, Voyager was 149 astronomical units from the Sun. Its magnetometer detected a sudden increase in magnetic field strength. The field jumped by roughly a third. At the same time, the proton density increased by a similar amount. A pressure front had reached the spacecraft. Scientists called this event the second pressure front, or PF2. Earlier events had produced increases. However, they did not behave exactly like this one. After PF2, the field did not quickly return to its previous level. It continued climbing as Voyager moved farther outward. The field eventually reached a peak near 0.56 nanotesla. Then it settled toward an elevated level close to 0.5 nanotesla. The enhancement lasted from 2020 into 2022. It covered a distance of several astronomical units while Voyager continued drifting through the thin plasma. This extended feature became known as the magnetic hump. A hump may sound like a small bump on a graph. In reality, it represented a large-scale structure in the space surrounding the solar system. Something had compressed and reorganized the magnetic environment far beyond the heliopause. The event raised a question. How far can the Sun's activity reach after it appears to have reached the edge of its territory? Recent simulations suggest that global changes in the solar cycle can create these distant magnetic structures. The solar wind is not perfectly steady. It rises and falls with the Sun's activity. Those changes can launch broad compressions that move outward, reach the heliopause, and continue into the VLISM. In other words, Voyager may have been measuring a delayed record of the Sun's past behavior. The disturbance it detected in 2020 could have started years earlier near the Sun. Space separated the cause from the effect. The spacecraft was not only observing where it was also reading an old message written by the Sun. If this is the kind of hidden space you want to understand, support the channel by leaving a like. Your click helps keep these deep space stories alive and tells the algorithm that science still deserves a place. If you know someone who thinks Voyager only takes old photographs, send this to them. The magnetic hump eventually faded, but what came afterward may be even more puzzling. Since roughly 2022, Voyager has been moving through what researchers describe as a remarkably calm post-hump region. The magnetic field fluctuations became smoother, sudden spikes became less common. The statistical pattern began to look more like a quiet, well-mixed system than the turbulent environment. That change created two competing interpretations. The first is dramatic. Perhaps Voyager has finally crossed into a new region. This region would be less controlled by the heliosphere and closer to the undisturbed interstellar medium. If so, the Sun's influence may extend much farther than the heliopause itself. The second interpretation is more subtle. Perhaps Voyager has not crossed into a new permanent region at all. Perhaps the magnetic hump acted like a filter. It may have absorbed, rearranged, or weakened disturbances traveling outward from the heliosphere. Behind it, Voyager could be passing through a temporary wake. The earlier turbulence was simply filtered out. The difference between these interpretations is enormous. The structure of the protective bubble may be larger than expected. The heliosphere could influence the interstellar medium across dozens of astronomical units beyond the boundary. But if the calm is a temporary wake, then the spacecraft may eventually encounter another change when new solar disturbances arrive. The quiet region would not be a final border. It would be a phase in an ongoing cycle. Space around the solar system would behave less like a fixed shell and more like a constantly changing flow. This is why the newest research is important even when it does not provide a final answer. Science is not only the process of announcing discoveries, it is also the process of measuring a strange result. Researchers build different explanations, test them against data, and admit when the evidence is still incomplete. The word unexpected does not mean the laws of physics have stopped working. It means old models were missing details. Physics books are not wrong because they fail to describe every place. They are incomplete because nature is specific. Voyager is revealing those missing details one thin signal at a time. Think about the scale of the problem. The spacecraft is moving through plasma so thin that it would be called an excellent vacuum by everyday standards. Yet that tiny amount of material still carries waves, pressure, magnetic structure, and energy. A region can look empty and still be physically active. This is one of the most important ideas. Emptiness is not the same as nothing. Between the stars, particles may be sparse, but fields stretch far. A shock wave does not need a thick atmosphere. A magnetic field does not need visible matter. A pressure front can travel through a medium that appears blank to human eyes. Voyager's instruments are designed to detect these invisible properties. The magnetometer measures the magnetic field. The plasma wave system listens to oscillations in the surrounding plasma. Other instruments once measured particles. Together, they transformed a remote theoretical region into a place with a timeline and a texture. But every measurement now carries a second story, the story of survival. Voyager 1 was never designed for this. Its original planetary mission was expected to last only a few years. The spacecraft has continued for decades. This is due to careful engineering, clever repairs, and decisions that would sound impossible. Its radioisotope thermoelectric generators convert heat from decaying plutonium into electricity. The supply decreases over time. The spacecraft loses a small amount of energy each year. After 50 years, small losses become serious limits. Engineers must choose which heaters to keep warm and which systems to switch off. Voyager has already lost several science instruments through deliberate shutdowns. Those decisions are painful. Every instrument removed means one less way to study an environment no other spacecraft is sampling. The remaining power is precious. A heater can protect a fuel line. A transmitter can send data. A scientific instrument can reveal a new physical structure. The team must balance all three. A spacecraft this old does not offer unlimited options. It offers a shrinking set of choices. Each choice affects the years of science still possible. There have even been plans for a Big Bang operation. The goal is to free enough electrical capacity to keep valuable instruments operating longer. If the approach works, Voyager could continue returning measurements into the 2030s, though nobody can guarantee that. The uncertainty is part of what makes every new data point feel important. A measurement from Voyager is not just another line in a database. It may be one of the last readings. It comes from the only human-made instrument currently inside this distant region. The communication challenge is extreme. Voyager's data rate is tiny by modern standards, around a few hundred bits per second at best. A single photograph contains more information than the spacecraft can transmit quickly. Scientists must decide what to measure. Then, the signal begins its journey home. It crosses billions of kilometers. It arrives at a dish antenna. It is separated from noise. Engineers check whether a strange value is real or a problem in the spacecraft. Only after all those steps can researchers begin asking what the data means. That is why a discovery from Voyager can take time to become a scientific paper. The spacecraft is not streaming high-definition footage. It is sending a fragile sequence of numbers. Researchers combine those numbers with solar observations, simulations, and data from missions closer to Earth. The result is a strange partnership across space and time. Voyager is measuring the environment from the outside. One spacecraft gives direct readings of plasma. Another maps the boundary using neutral particles. Together, they help scientists connect the inside view with the outside view. That connection matters. The heliosphere may shield the solar system from some high-energy particles arriving from the galaxy. Its shape can affect cosmic ray access and the way stars interact with their galactic surroundings. Every star with a wind may create a similar protective bubble. By studying ours, scientists learn about all of them. The sun becomes a laboratory. Voyager becomes the probe that reached the laboratory wall and kept going. There's also a lesson here about how discovery really happens. Before Voyager, we did not have a map. Then, a small machine crossed the boundary and exposed the difference between a prediction and a measurement. The surprise was not that nature broke rules, but that nature contained more layers than we expected. A map can be accurate and still incomplete. A theory can be powerful and still miss a feature. When a spacecraft reaches that place, the unknown does not become less real because humans failed to imagine it. Voyager's journey is also changing the meaning of distance. We talk about the edge as one simple location. But which edge do we mean? The last planet? The heliopause? The magnetic influence? Each definition points elsewhere. Voyager found signs that the sun's influence did not end at the heliopause. The edge was a transition. The spacecraft is in a region shaped by both the sun and the galaxy. And the most powerful part is that we are watching the interpretation change while the mission is still alive. Researchers are continuing to debate the measurements and wait for the next disturbance. A future cycle may send waves. When it arrives, it could help distinguish whether the calm post-hump region is permanent or temporary. Take a second to look at the subscribe button as if it were Voyager's last blinking light. If you want to be here when the next signal changes the story, turn it on now. Then share this video and ask one question: how can empty space create a wave? If that next wave reaches the spacecraft, the data may take nearly a day to arrive. The sun will change first, the plasma will carry the message, Voyager will detect the response, Earth will receive the signal later, and scientists will add another piece to the puzzle. That is the rhythm of this mission: eruption, travel, detection, delay, interpretation. At some point, Voyager will become too weak to communicate. The signal will fade, the spacecraft will continue moving, but the conversation will end. There will be no dramatic explosion, just a missing transmission followed by silence. But silence will not erase what Voyager found. It will remain in decades of measurements and in maps of the local interstellar environment. The spacecraft will have turned a blank space on a chart into a scientific destination. Future interstellar missions may travel faster and carry stronger instruments. They will stand on Voyager's foundation. The first measurements came from a machine built in the 1970s. It only needed to keep going. So what did Voyager 1 actually enter? It entered a newly observed layer of reality. Scientists can give it a name, but no single label captures the whole place. It still remembers the sun. It is outside the heliosphere, yet shaped by it. It is almost empty, yet carries waves. It looks calm, yet that calm may be temporary. It forces physics to become more precise. A textbook gives you the map. Voyager shows you the weather, and the weather is active. Voyager 1 is still sending home evidence that the space around our solar system is dynamic and layered. Its weak signal is still crossing the darkness, carrying a message from a place that once existed in equations. When you look at the stars, they may appear separated by emptiness. Voyager tells us otherwise. It has currents. It has pressure. It has memory. It has boundaries that behave like living interfaces. Somewhere far beyond the planets, a small machine built before most of us were born is still moving. Its journey is a reminder that the universe does not become ordinary just because we draw it on a page. The darkness between worlds has a structure of its own. There is a human side to these measurements too. Every command is a decision made by people who know the spacecraft may not answer forever. Is the instrument still healthy? Did the command work? Engineers repair it with planning and timing. We are watching an old machine continue to do one impossible job, carrying human curiosity farther. If this story changed your perspective, leave a comment with the detail that surprised you most. Subscribe for the next signal from the frontier and share this video. Voyager 1 may eventually fall silent, but before it does, it may encounter another result that forces us to redraw the map. And when that next message arrives, Earth will listen because interstellar space reached back.